Howdy, everyone. Hopefully, you're seeing me. I should probably check YouTube. Well, we got clear skies, we got a working telescope, and we got, stuff to look at. And so I decided, well, I was going to take some images of Messier 3, or the third object in the Charles Messier catalog, and I thought I'd give you guys a glimpse of it. I'd probably only stream it for about an hour or so while data collection or more. Internet connection is shite, and so this is probably going to be choppy, assuming you can actually hear me or see me at all. So I'm going to check YouTube real quick. You go away. Really bad internets. Scratch. Got a haircut today. It's a little scratchy. Let me see if I can do this. So, also apologize for the camera. I brought in a camera from my office. I'm in the control room of the observatory, and so yakety smackety. Actually, let me check it on my phone. So it's a little off kilter. Seems like it's working. Seems like it's working. Okay, I'm going to assume that's working. I'll just mute this, maybe. What if I do this? All right, I'm going to mute it. And just go with it, man. Just go with it, baby. All right. Or how about this? No, I don't want to hear myself talk. So if you come on and you ain't hear nothing, then let me know, and I will see if I can fix it. But yeah, the internet is really bad for some reason. So yeah, there's that. Okay. Getting my George Mason approved water. Getting this action going. I'm going to do this. And I'll lean back a bit. All right, so for posterity, what is I'm doing? Well, what I was trying to do is image the third object in the Messier catalog, which specifically is what you're seeing on the screen. This is a globular cluster. I'll get into that in a moment. So I'll just start off by talking about Charles Messier. I don't know too much about him, but what I can say is that one of the more famous star catalogs bears his name, and that is the Messier catalog. Messier catalog came about because Charles Messier was attempting to make a name for himself as a comet hunter. And he kept basically seeing the same fuzzy objects pretty much over and over again. And so what he wanted to do was to essentially create a catalog of not comets, so that he knew when he pointed his telescope at a particular area, he would check that catalog and say, oh, all right, I've already looked at this object, this little smudge. I've already looked at this smudge, and I've concluded that it's not a comet. The way that he concluded it wasn't a comet is that it did not move relative to the rest of the stars, at least not as long as he looked at it. A comet, you would expect it to do so. You would expect that the comet is moving relatively quickly through the solar system. So in comparison to the background stars, you should be able to notice it from a change from night to night. As far as I know, Messier never found a comet, or if he did, he's really not known for it. What he is known for is the 100 and, oh, I'm going to mess this up, 81 objects that are in his catalog. These compose some of the brightest, what I call deep sky objects. These are objects that are not single stars. Now, there is one binary in the Messier catalog, but for the most part, everything else is either a galaxy, a planetary nebulae, a globular cluster, or a open cluster. So pretty much these are objects that, and they are certainly objects you cannot see with your naked eye. You must have at least a pair of binoculars in order to view these objects. But a telescope like the one we have here is a much better fit. So, yeah, and I've been looking around. One of my favorite objects to image is a globular cluster, or at least, better, is a globular cluster, or at least with the optical setup that we have here at the observatory. For those of you who don't know, here at George Mason Observatory, we have a 32-inch Ritchey-Chrétien Cassegrain telescope. What all that means, in layman's terms, is that we use a pair of mirrors to focus the light onto a digital camera, which you can see on the screen. The largest of the two mirrors is 32 inches in diameter, or roughly 0.8 meters in diameter. For, don't want to be measuring telescopes here or getting into a telescope measuring contest, but a 0.8 meter telescope is on the very low end of, you can think of it either as a very, very low end research quality telescope or a very, very, very high end amateur scope. Really depends on how much money you want to throw around. Ours cost, just the telescope itself cost, I want to say $50K, somewhere in that neighborhood. The dome cost another $200K. And then you've got the price of all the infrastructure involved in that as well. And you can definitely spend more if you wanted a really snazzy high-end telescope, like 36-inch, for example, rather than 32. You could easily spend $1 million on it. There is a fairly wide range in price differential between one manufacturer of telescope to the next. So, but in any event, this telescope fits a very interesting niche, which I think is going to become more useful as time goes on. Maybe, I don't know. I might be overstating this. One of the things we do here at George Mason is we look for exoplanets, we attempt to confirm the existence of exoplanets that have been identified as candidates using the Space Telescope tests. And the way we do that is we use the transit method of planetary detection. If you want more specifics on that, please see one of my lectures on, I think it's formation of planetary systems. In there, I talk about specific exoplanet detection methods. Anyway, in brief, what it is we look at a star for an extended period of time, and we see if the brightness of that star changes by a certain magnitude or a certain amount in a certain way. If it has a specific brightness change signature, it dips in a certain way by a certain amount, then we have confidence that at least I should say that we have an indication that there is an exoplanet revolving around or orbit, revolving around that star, periodically moving in between our line of sight and blocking out some of that light from that host star. Hence why the brightness drops. And so big telescopes like Keck, Gemini, JWST, or whatever, they're real good at finding these candidates, but they ain't so good at follow-up observations, because what we want to be able to do is you need to be able to, in science, you need to be able to confirm something. You need to, and the way you do that is by follow-up observations, typically through other facilities, other telescopes, using other telescopes, other systems, so that you can rule out any kind of error or any kind of detection bias or anything of that nature. So the signal is you can rule out that the signature that you're seeing, the brightness change that you're seeing, is not from the telescope that you're using. If many different telescopes using many different types of cameras and optics see the same signature, then you definitely know that it's not the telescope doing it. And in exoplanet science, one of the more interesting questions, or at least I think from the public standpoint, is, Earth 2.0. Is there a habitable world out there that looks like Earth? Well, what we can say is that there are rocky planets that are of Earth-like mass, mainly through these transit detection methods, the same methods that we do here at GMU. The only problem is that most of these systems, most of these planetary systems that we've studied, we've only been studying for less than a year. We only have less than a year's worth of data, meaning that if you do have an Earth-sized planet going around that star, you may have seen it once, or you may not have seen it at all, simply because you weren't looking long enough. So that's where we come in. For one, we can, not like I said, we can confirm, we can follow up with observations. Or if we wanted to, we could, and telescopes like our own, and there are actual professional setups done, or when I say professional, I mean research, intended for research publication setups that are doing this, doing longitudinal, long time frame observations, and doing long time frame observations, so that we could potentially see the signature of a planet like the Earth going around. Now, for me, I tend to, when I look at binary stars or I look at variability, one of at the very least, I like the power of 3. If I can see that signature 3 times, then I know then I have confidence that at least it's real, that it's physical in some nature. It may not be a planet, or may not be a binary star eclipse, or a variability event, but I know that is repeatable, that it's not just some fluke or random thing. So if we were to look for an exoplanet Earth 2.0, then what that means is we have to look for at least 3 years. And that's assuming that we see it right off the bat. So in order to find these exoplanets, these Earth 2.0s, we expect them, because right now there are a lot of studies that are done on stars very much like the sun. They refer to them as sun-like stars. If we're going to find Earth 2.0, it's going to take us a while, simply because of just the physical constraints. We have to wait for that planet to go around at least once, or in my case, and I think there might be even tighter constraints among the people who do this really for a living, more than 3 times or more in order to see this. With transit, again, you need 3 revolutions in order to see that observational signature. Radial velocity is a little bit, Doppler is a little bit more forgiving, but still, you're talking about at least a couple of years in order to get possibly see that signature, assuming that it's actually detectable using Doppler. So for telescopes like our own, like the one we have here at George Mason, I think they are going to fill that niche, that where we're going to start developing programs, research grade programs that are just long term. We pick some stars, we stare at them for years, and we see what's going on. Now, it might not be that might not be the case, or may not be the case, because telescopes like Vera Rubin are coming online very, very soon, like within the next year or so. And they're going to be doing large synaptic surveys. What that means is they're going to measure they're going to look at the entire night sky to a certain depth, a certain faintness limit. And they're going to and that telescope is going to look at the sky, complete northern hemisphere, or complete sky that it can see. It's in the northern hemisphere. It's near Seattle, if I remember correctly. And it's going to do that over the entire sky in 3 nights. It's going to continue to do that for years. So it certainly has the capability, the time frame to find Earth 2.0. The issue becomes then how are you going to sift through all that data? We're talking about, I think it's terabytes a day. So I'm kind of just rambling here. Let's get back to what I'm looking at. So what are we looking at? Like I said, we're looking at Messier 3, or the third object in Charles Messier's catalog, or M3, as it's more commonly known. M3 is a globular cluster. I feel like I've done this before, because some of my earlier imaging vids or streams were on globulars, because, as I may have mentioned, I love looking at globulars. I don't know what it is. Globular cluster is one of the first cohesive, organized structures that formed in the galaxy. We believe that the prevailing hypothesis for how galaxies form is you start off with this large dark matter halo, or a clump of dark matter, which then, as it collapses due to gravity, it brings light matter, baryonic matter, what we might consider normal matter, along with it. And then gravity latches onto that, and the light matter collapses even further. And as it does so, it starts to form stars. And not only that, but it forms stars in localized regions, which form clusters. So the first stars form in these giant clusters, and they are gravitationally bound. And the reason why they're called globular clusters is because if you have enough mass in a sufficiently small area, then gravity is going to rearrange things such that it becomes a sphere, or sphere-like. And you can kind of see this, and this is also another kind of good example of what we mean by a centrally concentrated object. If I play with I'm going to wait until it downloads, and then I'll play with it. All right. So if I'll play with this, I can adjust the contrast essentially, and by doing so, you can see, hopefully, that the inner region of this globular is far denser in population than the outskirts. And all these little dots faint dots you can see out here, all of those stars, or I would bank that most, if not all of those stars, are actually associated with the globular cluster and not further back. You would need a different type of study in order to figure that out. But that's beyond the scope of this. For now, just trust me and say that those stars are in fact inherent to gravitationally bound to that globular cluster, and not further away or somehow close in. But this is centrally concentrated. So this demonstrates basically the rudimentaries of gravity, and that gravity is distance dependent, and it's distance dependent as the inverse square. So if you're closer, then you feel the the amount, if the force squares. So if you're twice as close, you'll feel 4 times the amount of force, or 4 times the gravitational effect, than if you're half as far away, or double. I'm sorry, double that distance. So that produces a essentially concentrated object where you have really dense, a lot of stars in the center, and then the density slowly drops as you get further and further out. And we can see that if I adjust the contrast here. Oops, I think I'm going the wrong direction. Oh. And if we blow out the contrast, we're going to blow out the center region, and we have, you can hopefully, I've brought out some of these fainter stars on the outskirts. Now, are all of these stars in this field of view part of this cluster? No, certainly not. I would put money on that this star, at the very least, is not. That star certainly isn't. This is more intuition than anything else, because I know basically these stars are way too bright. If they were at the same distance as these stars, they would have to be very young and very massive, basically very massive, to be that bright. And based on what a globular cluster is, they can't be. Howdy, Chris and Clive. This is a little bit kludgy setup. I am looking at the chat on YouTube on my phone. I am currently in the control room of our telescope. The internet sucks, which is why I probably appear choppy, sound choppy, and because why I'm not VNCing into the computer from, say, my computer downstairs, or more comfortably, that's a word, from my home. So yeah, so we're looking at M3. Globular cluster. This particular cluster, I don't know the specs on it. I'm sure we could Google it, and Messier 3, but in general, a globular cluster has about a few 100,000 stars in its population. The largest ones, like M13, the Great Cluster, and Hercules, they number in the low millions. So these are large star clusters. These are the largest, like I said, the largest cohesive structures of stars that are in a localized area that are not galaxies. In order to get anything larger, then really you're going to have to look at the galaxy as a whole, or rather the arms of the galaxy. Anyway, hopefully you get the point. These are old, and these are large. And so all of these stars are, roughly speaking, because they formed first in the galaxy, these stars are on the order of 10 to 12 billion years old. These are essentially the second generation of stars. There was a first generation of stars that formed very early on in the universe. They lived for maybe hundreds of thousands of years and died off and blew off their material out into space. And then the dark matter brought that material back into another area, and that collapsed and formed this population of stars, which we have called POP1. How many aliens has Rob found? Yeah. I signed an NDA. I can't say much about the aliens. I really, or they may be turning our frogs gay. I don't know. I can't say one way or the other. Or the government will get me. So that's basically what our globular cluster is. And one of these days, and honestly, I probably will take this data set and hand it off to the students who have more time than I do. Maybe over the summer, I'll do something with it. But yeah, ultimately what I want to do is I want to create a snazzy 3-color image of M3. And really what I want to do is I want to be able to, so astrophotography is not easy. Astrophotography is not easy. Let's just put it that way. Now, there are two general ways that you can do astrophotography. The first is usually what you see in glossy magazines, and amateur magazine, where you have these giant nebulae or giant star forming regions. You have views that are on the order of a few degrees in size, or a few full moons in size, or many full moons in size. You have these beautiful pictures of gas and stuff going around. That is typically done with a modest rig. Roughly, the ones I've seen are typically around 8 inches in size or in aperture. Some go up to 12, 10. Others that you can do them with smaller apertures. You can actually do them with small refractors. The optics are good enough. You can do it that way. But they use DSLRs. They use nose bother. They use essentially a color camera. It's a CCD camera, very much like the one you're seeing right now, but they can image in real color, as opposed to what I'm doing. And honestly, what Hubble did or does, and what JWST does. Hold on a second. Whee! And he's back. What I'm doing, and like I said, what Hubble does, and what JWST is doing, is imaging through filters. So the camera itself is black and white. It's grayscale, essentially. And what we do is that we look through, or we take images, individual images, that are in certain, for lack of a better term, a color, a certain range of wavelengths, which correspond to a certain color of light. Now, in this case, that is quite literally true. I am doing, this is optical. This is the optical part of the spectrum. So I'm using 3 filters. I am using I'm using the visual Johnson V filter, the Johnson Cousins R filter, and a narrowband H alpha filter. What that means is that the V filter looks primarily at the green part of the visual spectrum. The R filter looks primarily in the red part of the optical spectrum. The H alpha filter looks at a very particular, very small region within the red, but on average, it's redder than the red filter. Thereabouts. So I have 3 colors. Now, I can then, so I have images right now. This image is my red filter. This next one coming up is loading. Oh, I'm sorry. Oh, I forgot to check that. It's doing R. It's doing all the reds. So these are all the reds. The next ones will be H alpha. Anyway, so you have to take my word for it. I have taken all of my images in green. I have now taken all of my images in, all of my images in R and red. The next 15 will be in H alpha. And then I will take those images and I will combine them into a 3-color image. Now, I'm not a photographer, not an artist, but what I can say is you have the 3 primary colors: blue, green, and red. And from my understanding, you can make any other color from those 3 primary colors. So if you have a blue image, a green image, and a red image, and you combine their levels in a certain way, you can get any color you want. And so that is how you can take a 3-color image and create a true color image. And by true color, what I mean is that is what you would truly see with your eyeballs if you were looking at it through, a telescope or binoculars or whatever. Oh, wow. That looks poopy. That is H alpha. Like I said, narrow band, so not as much light is getting through as the other filters, which is why it looks way different. But I didn't think it was going to look this way different. Well, we'll see how it goes. Yeah. Okay, so full disclosure, I like astrophotography, but I kind of suck at it. And one of the reasons why I suck at it is I don't really plan. I'm not a planning sort of dude. This, like I said, it was basically off the cuff. The telescope wasn't being used. Clear night. Sadly, iffy internet. But I was like, hey, let's try to image something. And first thing, I was looking through the sky and I was like, hey, what's cool to look at that I can look at through this? Globular. And I found M3 and I was like, hey, let's go for it. Kind of going back a step. You know, those glossy images that you see and that are not taken with Hubble or JWST, they're taken by amateurs that are using a DSLR. They are wide field. Those are many degrees square. And so for objects like all the pretty objects like gas clouds, open clusters, things of that nature are wide field. You need a large field of view in order to look at them. Our telescope is not wide field, is not a large field. It's an f8 for those of you who know anything about focal ratios. And so our field of view is roughly the size of the full moon. It's actually a little smaller. It's 25 arc minutes squared as opposed to the 30 of a full moon. So I'm really limited in what I can image. And so the cool things are, and so I'm limited to basically certain bright planetary nebulae, globular clusters, and galaxies. We can technically do planets, but we're talking maybe 4 or 5 pixels across the surface of Jupiter. It's really not. It can be very colorful, but it's not, setting the world on fire. So I'm limited that way. But the reason why I suck at this is, so there are a couple things that you need to take into account when you're doing this. The challenges for globulars is if you want a good globular image, you want to be able to capture the outer edges of that globular cluster, those faint those faint outer stars, without blowing out the center. So, and what I mean by that is I kind of showed that earlier. Blowing out the center means, nope. Blowing out the center means that this is really bad. Is the center stars are so bright that they basically blend into a blob. Because the problem is, while the wells, not the Clive wells, but the wells of the CCD can register counts between 0 and 65,535. They can only be described or shown through 255 channels. So you've got to scale it. And that's essentially where that contrast comes in. So the way to do this, in theory, is you want exposures that are long enough that you can see the background star, or not background, the outer stars, but not so long that the inner stars are so bright that they saturate and blur into each other. And then you take these images, and right now I'm taking a set of 15, depending on how I feel after this is done. I might take another set. Once you take multiple exposures, like I said, in this case 15, you can stack them on top of each other. What that does is that the signal will add in a linear way, but the noise, the speckling that you see on that image, that's primarily noise, electronic noise. That noise is random. And so if you stack 2 random images on top of each other, they're going to average out. Essentially, the total brightness of that is going to, or the total brightness is going to drop to a certain average value. And so, and you can do the math, and what you find is when you stack these images on top of each other, while the signal is linear in growth, the noise is 1 over square root in growth. So overall, your signal gets better and your noise gets tamped down as you add. So that helps in seeing the fainter stuff and combining them together and being able to, in like Photoshop or GIMP or what have you, being able to combine them. So you need to be able to plan your exposures well, which in this case I didn't. My H alpha images are way too faint. So I don't know what that's going to do. Well, it's probably going to make my images on the back end greener than I would like. So I don't know. So yeah, so that's one of the reasons why I suck at this. The other reason why I suck at this is because it's Photoshop. Of course it is. When you take these 3 images, when you take images that are taken from a blue filter, a green filter, and a red filter, you got to combine them, and you have to do so in a way where you balance the colors. Now, there are ways to do this in a quantitative fashion. What you do is you look at a star of known color, and you basically then can set the levels of how much blue to include, how much red to include, how much green to include, based on that reference star or reference stars. I don't have a very good way of doing that. I'm sure there is a way of doing that, but I haven't figured it out, and I haven't put the time in to figure it out. So for me, it's pure guesswork as to, and it is what we call in the professional realm Kai by eye. Hey, look, it looks good. Oh, I wonder if I'm getting clouds. I wonder if it was cloudy during that, or cloudy, high level clouds through that. So yeah, so it's guesswork for me. It's quite literal guesswork. I put it together until it looks cool. Is it true color? Probably not. This certainly will not be. This one is, these are taken in, like I said, the green, the red, and the really red. And so they're going to mimic. The green is going to go into the blue channel. The red is going to go into the green channel, and the really red is going to go into the red channel. And I'm going to combine them, or my students are going to combine them. And I hope a spider is not crawling on me. I saw a spider crawl across the monitor over there. I'm like, no, I feel like I'm being called on. So yeah. So in that way, so this one, the resultant image, whatever it is I get out of this, which if it looks any good, I will definitely, put up. I may do an entire stream based on my astrophotographic work, my gallery of images, assuming I can find. I've had some data loss, so I don't know. Anyway, I'm babbling at this point. So maybe I will do that. I thought about doing a stream where I basically do a photo photography lesson, how you would combine these things. But honestly, I suck so bad at it that I really don't want to mislead anyone. There are folks on the internet who are way better at it than I am. You should go check them out, their YouTube channels out. What they don't have, what I have, they don't have, is access to a telescope this large. I have a large telescope. And so I can get images that, fainter image. I can see fainter than they can, than they potentially can. So yeah, and I can show you the exciting world of astronomy in real time. And yeah, this is it. Woohoo! You are looking at, if I were to do science, if I were to basically be looking at this globular cluster for scientific purposes, this is the procedure that I would do. This is how I would collect my data. Is I would figure out the exposures. Of course, not in this sense. This sense, I didn't figure out the exposures too rigorously. But prior, if I were doing real science, what I would do is I would spend some time to figure out what my optimal exposure lengths would be to get as much science or the best quality data the fastest that I could. And I would set the exposure times, and I would basically set it and forget it. Put it in here. I basically tell it, all right, I want 50 green images with an exposure time of 5 seconds. I want 50 red images with an exposure time of 10 seconds, yada, yada. And I just set it and let it go. And I sit here and I wait and I check out. And I just monitor it to see whether or not the telescope catches on fire, if clouds come in. And really, we've gotten to the point now, particularly here, and especially here at GMU, some of our students have actually written code where this whole thing gets automated. They just tell it at the very beginning of the night, I want you to look at this object in these filters for these sets amount of times for this long. Go. And then they go to sleep. So we've got safeguards in place that if it starts to rain, we're connected to a weather station. And so the code monitors, gets data from that weather station, and then it basically literally shuts down, closes the dome, puts everything to bed if the chance of rain gets too high. If the humidity gets too high, does the same thing. So yeah, exciting stuff. Really exciting stuff. What I might do, because this is so exciting, is I might choose a different object. I might look for another object that's not a globular cluster to show you. The other issue I'm looking at is I found out tonight that I need to look at my calendar far more in advance than a day, and the day of, and because I've got two public teaching or public events tomorrow. So one of them starts at 9:30 in the morning, and so yeah, I've got to be awake enough to give Dr. Rob's trademarked Tour of the Universe talk. And I have to do it I have to do it coherently. At least I'm sure they would want me to. I think the first group is I think both groups are high school students. God, I hope so. Clive, I'm not hiding the alien pics. I cannot say for certain whether I may not have alien pics. I don't have alien pics because if I had alien pics, then that would mean that aliens exist. And, I couldn't say that either way. I couldn't admit that aliens exist. It's not, I'm contractually obligated. Part of my NASA stipend is stipulated. The stipend is stipulated. Part of it is stipulated that I do not reveal the existence of an intergalactic federation. Or anything like that, So I can't, I just can't do it. The money is just too good. I get like $54 million a day for my NASA stipend. It's outrageous. It's amazing. All astronomers do, by the way. Yeah. We all get money from NASA to definitely not hide alien pics, because we would never do that. Never do that. I think I need some water. So how y'all doing out there in interwebby land? Looks like I got 2 more H alpha images. Once that's done, I will at least, at the very least, I will take this down, and I will show you the interface that I use to move the telescope around, and we'll just see if I can find another interesting object to take a couple pics of. Tour the universe. Start with the Big Bang Burger Bar and end up at the Milky Ways, the restaurant at the end of the universe. Of course, I will stop at the restaurant at the end of the universe. Which courses do I teach at GMU? That varies, but typically I teach ASTR 103, which is the Survey Introductory to Astronomy course. I cover everything that covers everything in astronomy, from planets to galaxies to the universe. In fall, I also teach ASTR 302, which is Introduction to Cosmology, which is a qualitative course. We do go into a little bit of math, but it's primarily a description of cosmology rather than a rigorous study of it. And then on top of that, I will teach astronomy labs, ASTR 111 or 112 or 114. This semester, I started teaching physics recitations. Over the summer, I'm also going to be teaching physics recitations. I like doing that. I like doing those. Between you, me, and the internet, I actually prefer them to teaching astronomy labs because I don't know. It's one of the things that's fantastic about physics is you feel productive when you work through a problem. When you work through a problem and you're able to explain step by step how that problem or how that the problem solving, how the problem was solved through those steps, there's just something gratifying to it. It's by the numbers in a way. So physics 160 recitations. Yes, actually. I am teaching 2 of those this semester. Over the summer, I'm going to be teaching physics 234 recitations. And in fall, I don't know. There was some weirdness, or there was not weirdness. There is a reason why I am not teaching ASTR 103 this semester, and why I'm teaching physics recitations instead. Whether or not the reasons for that continue into fall and maybe into perpetuity, I don't know. I haven't been told. But Peyton, yeah. I would like to continue to teach physics recitations at the very least. I'd actually like to teach physics 160, but I think the demand for that is, I think there are other professors far more senior than I am who are in line to teach that course. So, oh, howdy, Tina. I didn't see you. I didn't see you there, lurking like you are. Oh, all right. This is done. All right. What are we doing? For those of you who don't know, yeah, the reason why it looks all weird is I'm actually doing this in kind of a kludgy way. I am doing this in the control room of with my camera. There's our stuff. There's our webcams, our mandatory poster of Einstein, our mandatory board, which illustrates extragalactic or extra transiting exoplanet stuff and random other stuff. So yeah, that camera gets hot. You might be asking, what's up with the mood lighting? Oh, first, what's up with the shirt? You can't go wrong with a Godzilla Hawaiian shirt. It's just impossible not to have a good day while wearing a Godzilla Hawaiian shirt. It's just not possible. The mood lighting actually has a physical reason. Stupid camera. Earthquake. Sorry for the motion sickness. All right, so better. The mood lighting is because astronomers traditionally observe in red lighting in order to be able to see. Blue lighting or white light is too energetic. Basically, it kills your night vision. So, jealous of the shirt? Yeah. My best friend, who's a brother to me, got this shirt for me. he was looking for shirts for his one of his young ones, and he saw this and he was like, "Oh, I've got to buy that for Rob." So he did, and he sent it to her. So Gojira, you just can't go wrong with Gojira. All right, what are we doing here? Da-dum, 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 da-dum. All right, I'm going to have to switch over. Oh, you can go away. And I am going to do this. Present. Share screen. Window. That one. Oh, and howdy, Matt. Haven't seen you in a while. Hoping you've been doing well. This is the Sky. La, la, la. The Sky program, which is in its basic form is a planetarium program, very much like Stellarium. But in its snazzy pro form is just this camera is annoying me. In its snazzy pro form, it can actually control really your entire observatory. It's designed to be able to control your dome, your telescope, any cameras that you attach to it, weather stations, you know, so forth and so on. We actually do most of that stuff control with other programs. The Sky for us is primarily just a telescope. It just moves the telescope around. So right now we are looking in the constellation, near the constellation of Biotes. This is Arcturus. This is M3 or NGC 5270. What is that? 72? 72. 5272. Very romantic name. Let's M53. Let's pull out here a little second. That's what you said. We have Hercules, M13, the Great Globular Cluster, but I'm going to try to show you something that isn't a globular. So, have you attached a P900 to your telescope? No, I haven't, actually. What I would... I'm obsessed with you guys being able to see my face. No, but what I would really like to do is I would like to actually attach some kind of DSLR. I know that was made as a joke, but I would really love to actually attach some kind of three-color, true color imager or camera on this thing and see what it can do, or at least slap one of those onto the 8-inch, one of the 8-inch telescopes, or preferably one of the 12-inch telescopes to see what it would look like. All right, now that I've got that up, I'm actually going to, and the stream seems to be stable. All right, what is M5? Messier 5. That one. A globular cluster. It's one of the things I love about this, about the night sky, is that there are effectively seasons. Obviously there's fall, winter, yada, yada. But from an observing standpoint, you really have two kind of seasons. You have globular cluster season and you have open cluster season. And we're leaving open cluster season and going into globulars. And the problem is that in open cluster season is also where all the cool planetary nebulae are. But there should be some galaxies popping in and out here. And what else can we look at? M92. What does that look like? What is that? It's a globular cluster. Jesus. I'm so not used to having globulars in my sky all winter that just kind of like, oh, they're all over the place now. It's amazing how the sky, as we revolve around the sun, how the sky seems to change based on where the sun isn't. Gumball globular. I will show you something other than a globular. Let's see here. I have an idea. Right. Galaxies. See. Stupid. There we go. What are we? Spring? We're in spring. Spring sky. Nope, that is in fact. How did I get to Google Maps? Good Lord. Spring sky. 19 galaxies. Woo. I like 19 galaxies. Andromeda set. Where's Sombrero? Where is the Sombrero? Go away. Yeah. Constellation of Leo. Perfect. M65. Perfect. Let's do it. Yeah. I'm excited. I don't think I've ever looked at M65. It's supposed to look like that. So there's some lovely dust lanes. So maybe we'll see something. I don't know. I'm excited. Our telescope is moving. Moving into position. I can hear the dome slowly creaking its sorry butt over. What's going on with my feed? Oh, there we go. Okay. All right. So that's gone there. Let's go over here. I'm going to stop sharing that, and I'm going to present. Share screen. Window. That one. All right, we're going back to this one. Okay. Let us do as I normally do. Let's see if we can find it. 10 seconds exposure in green. It's usually a good way of figuring out if an object is there. So, Gary, if you're watching this, I just did a very large slew across the sky, and hopefully I'm not going to embarrass myself here. Using an equatorial mount. And there it is. Really, really faint. Woo! Yeah, it's right there. Yeah. I didn't even check the size of this thing. All right. Let's go nuts. Let's see what this looks like. 2 minutes in R. Now, one of the reasons why we take images in different filters, there is a science reason to it. And the reason, and galaxies are actually a pretty obvious reason why, or a very obvious example of why. Is if you look in the blue, if you look at a galaxy in the blue filter, the thing that really pops out to you are obviously the blue objects, and those are going to be the giant molecular clouds, which are studied in the spiral arms of galaxies. If you look in the red part of this spectrum, and this is both optical, this is within what we would consider normal sight. If you look in the blue, the globular, not the globular, the giant molecular clouds, the star forming regions, they pop. If you look in the red, then you can still see the star forming regions, but they're not nearly as significant, or not nearly as in your face. But you can see the dust lanes, basically tracks of dust in the disk of the galaxy. And the reason why is because you are, as I said, you're looking at different colors, but what that really translates to from a physics standpoint is you're looking at different temperatures. So for blue, you're looking at things that are slightly higher temperature than things in the red. For in our blue filter, we would see things optimally that are around 10,000 Kelvin. In the red filter, we would see things optimally that were around 4,000 or 5,000 Kelvin. So, it's downloading, or it's going. I don't know if you can see the exposure time up here. It's now downloading. Dun, dun, dun. Hey, there it is. All right, so this is a raw image. Basically, this is what we call a FITS image, or FITS file, FITS. I used to know what that stood for. It's an acronym, obviously, but I can't remember. It is a raw data file. And so what we're seeing here, this bright point in the middle, is not real. I'm almost tempted to say it's vignetting, but I don't think so. At least I hope not. I think what this has to do more with is it probably is vignetting. It's either a problem with the quantum efficiency of the chip, or it is it's called vignetting. It's an optical effect of it's an aberration due to basically the optics of the telescope. In any event, this can be filtered, or this can be calibrated out. That can go away. This darker area right here, that is actually a dust mote somewhere in the optical train. So on one of these pieces of glass, there is a piece of dust that is causing that dark region. Yeah, man, it looks like, yeah, that's the thing is, it's definitely looking like vignetting, but I wouldn't think it would be that extreme. I can't, yeah. I'm going to have to look into that even further, because I've seen this effect before. This is not new to me, but I've never seen it this prominent. But there again, that might just be because of how it's scaled. Ooh. That's kind of nice. Oops. Let's do this. Let's really zoom in. So this is a pretty good camera. This is I think it's a 4K by 4K. And like I said, this is just a 2-minute exposure in R. And I hope you could see that there is structure there. This area right here, kind of that little feature off to the left of the bright central region, the bulge of the galaxy, that is the beginning, or the telltale sign of a dust lane. I think that if we did even longer exposure, that would really be pulling it out. But let me do a really crude histogram or scaling. See if I can pull this out any further. And no, I don't think I can. Yeah, it's a single raw image, but again, also, yeah, I don't know, there might be something there, but this is definitely an object I'm going to be coming back to, although it is teeny. I'd say that it's probably 1 arc minute by 5. Chris, good night. I'm probably going to be hanging up my my hat pretty soon. I might give this a good college try before I go, but true story of much irony. In CGI, we're asked to add vignetting to the image to make it seem more like film. Always makes me grumpy to deliberately corrupt my imagery. Yeah, that would irritate me as well. Um, yeah, but I really wish I would. And I don't know what this is. You can see here. There's also this darkening region, which almost looks like a shutter failure, as if the shutter hung for a little bit and then snapped open the rest of the way. Hello. There we go. Well, I don't know. I don't know how real that is. Doesn't look like it could be a couple hundred pixels or counts in that. I don't know. Maybe not. All right. How about just for giggles? Let's see what this looks like in blue. Now, I'm going to tell you right now the reason why I was doing green, red, and really red was that in the blue, there are a number of different reasons why you get the light that you do on the back end. Because of the detector and because of the filters that we use, we lose a lot of light if we look in the blue part of the spectrum. So what I'm trying to say is don't temper your expectations as to what this is going to look like. That's really for me than you. Like, I want this to look good. I want 120 seconds to be able to see something, a little something. Oh, these little squiggles down here that look like, weird bacteria. Those are, I know exactly where those come from, where they are. Those are fragments of a cotton ball that was used to clean the pane of glass right above the shutter. So that's why it almost looks like it's in focus. This dust mote that's right here more than likely is on the main mirror, if I had to make a guess. So, yeah. Do spiders ever walk over the end of the telescope? No, not that. Well, not that we have been able to image. The weirdest thing I've imaged is either a bird or a bat. Can never quite be sure. I think it was a bat because this was in Florida at Rosemary Hill Observatory, and there were a lot of bats for some reason, and we actually saw this kind of shadow across the image. It's really kind of eerie. And considering the field of view, that's pretty serendipitous. So definitely caught planes, no trains, no automobiles, but also satellites. We've definitely gotten satellite streaks through here. Quite a number of planes because we're right under the part of the holding pattern for Dulles, so we get a lot of planes. So is there anything new in Flat Earth world out there? I've been popping in and out of the Earth Awakenings and the Tartaria boards, and really seems that Mr. Whitsitt is basically taking it over. When there is really active conversation, it's usually him on one side of it. Oh, shoot. Is that the new image? Is that blue? Really should be paying attention. What is going on? I'm starting to wonder if this actually did anything at all. Why can't I access these menu? Ah, here we go. All right, or not. Just having problems. And a fun discussion with Flat Earth today. He insisted that NASA never provides raw images with EXIF data. Yep, that was nice. I think Maxim DL is being weird. I can't seem to access the menu bar so that I can look at the FITS data and figure out if that's a new image. I don't think it is. So either I didn't hit start or it hung. And it's really working to get down to negative 25C. One of the things that we have to worry about is what we call dark current. Basically, the camera is stupid, so it doesn't know if a photon stems from the night sky or the camera itself. And so the hotter the thing is, the more light it's going to emit in the region that the camera can detect. So the way that we try to combat that or mitigate that is to cool the chip down as much as we can. So right now it's running at 80% power roughly to get it down to negative 25C. I usually don't like my cooler powers greater than 50. Because I found with older cameras that actually adds photographic noise. It doesn't look like it's changed. What in the world? What is going on? Excuse me. Yeah, something is definitely off. Because it's at 120 of 120. So it should be downloading the image at this point, and it's not. We were having some connection issues earlier tonight, or at some point tonight. So I think that is a cosmic sign that I need to be going to bed because I really don't want to have to troubleshoot anything right now. So with that, thank you all for being here with me tonight. This was fun. I've really been wanting to do something like this for a while now. I did this a couple of times early on in my channel, and really have kind of not had the time or the opportunity to do this. And I'd like to actually do more of this later on. I'd like that to be a part of my channel where I do imaging of the night sky, or I take data and talk about the project that I'm doing. So, but anyway, let me stop sharing my screen and yeah, say goodbye to all of you properly. Yeah, again, thank you all for being here, and peace out, clear skies, and I should be, hopefully, as I mentioned in my lecture today, I'm hoping to put out a lecture every day for the rest of the week until I'm done with my solar system series. So right now, I just finished off Mars. The next few lectures will talk about planetary atmospheres and the Jovian worlds, and then the sun, and then I think, asteroids, comets, and then all in one lecture, and then the sun. So I think I will be done with my solar system lectures series in about a week, maybe a little bit more, and then I'll move on to extragalactic stuff. Well, and then in summer, we'll go from there. So that's basically all. I hope the aliens bring back your mustache. It is definitely coming back. I sometimes I wonder what my upper lip looks like, and so I periodically just shave it off to take it in. And but it will be coming back. My students said it looks better, or looks good, but they're my students, so what else are they gonna say? So I don't know. We don't know your astrophysics. Nice. Yeah. All right, Matt. So yeah, but yes, the stash will be coming back unless something radically changes in my personal life. The stash is definitely coming back. All right. Peace out. Clear skies. And good night.